Thank you. A very good afternoon. My name is Erik and I work at Zenseact. And at Zenseact we are focusing on this. Traffic safety. As you may know, traffic safety is a big challenge. Every year 1.3 million people die in the road transportation system. 1.3 million people every single year. And this is a top of an iceberg where there is many more people that get severely injured. WHO says 50 million people a year get injured. And of course, this is a huge problem for society. We have a traffic or road traffic system that is far from optimal. And this is something that we do not have to accept. We think we can do something about it. And we think we can use technology to help drivers avoid these types of collisions. So our motto is towards zero faster. We believe that we can use advanced tech to help drivers to get to a point where we have zero collisions. That's our target. How are we doing this? We are doing this by developing software for consumer vehicles that can help drivers to avoid collisions or that can even take over the driving. Where you have self-driving cars that are inherently safe, that will never cause a collision. And we use this latest trend in technology right now with self-driving cars, deep learning, which has really had a big impact on this, for building cars that can drive themselves, and when they are driven manually, that they can be super safe. So I think it will take a long time before all cars can drive autonomously all around the world at any point in time in all the different weather conditions. I mean, it will be a journey of decades. But we can start somewhere. And by building a very good business case of a consumer vehicle that maybe at a small operational design domain, maybe only a small portion of the time can drive autonomously, then we have a lot of tech in the car. You need the sensors, you need the compute, you need the algorithms. And once they're there, you can also use it when you're cruising or when you are driving manually. So we try to use this latest trend to get towards zero faster. Who are we? We are a company of around 600 engineers. Our heritage is within Zenuity, of which we were part in our previous life. Before that, many of us were working at Volvo Cars, where we started a journey of active safety 2 decades ago, something like that. It has been a long journey, but we really started from scratch at that time. I was fortunately to be one of them. And we built active safety technology. We saw it made a difference in real life. We are actually saving lives with this type of technology. But we started a company around this because it became so big, it became so important. And this company is called Zensec today. As I said, 600,000 engineers, most of them in Gothenburg, some of them in Shanghai. We are developing a software stack with Volvo Cars and Polestar as our lead customers. We will launch that next year. And beyond that, there is a lot more to come. So digging a little bit into that, what are we actually developing? We are developing something that we have called One Pilot. One Pilot is a set of software features that keeps you safe no matter if you drive, cruise or ride. So we're targeting premium consumer vehicles that you sometimes drive yourself, sometimes cruise, or sometimes can let drive for you. And in order to do that, you need, of course, a lot of different tech. And that's the tech that we are developing. Some of the tech is software inside of the car, onboard software, using sensors like cameras, radars, LiDARs on board. But those cars are connected. We'll be able to probe a lot of data from that car. Some of the software is being deployed in the cloud. So also that we do. So we built a complete system that allows you to do this in a very safe way. The paradigm that we use for that is a little bit different. The automotive industry has traditionally been very hardware focused. And car manufacturer would kind of source different hardware components, a camera, a radar, a control unit, and then they would kind of tie this together, but in a lot of different configurations. Because when people buy cars, I mean, you have to put all these crosses. I want to have this option, maybe not that, and then you have a lot of different variants. I think that era is over. Cars need to be defined by software instead of hardware. software will be so valuable and also so complex that you cannot deal with variance. We need to fight the software variance, and we have to adapt the hardware to the software. And this is what we're going to try now. We are going to put, or together with Volvo Cars, and I mean, they take the big hit when it comes to the cost of all that hardware, but they're going to put a lot of hardware as standard in the vehicles. Multiple cameras, multiple radars, a LiDAR, ultrasonic sensors. And if you want to take care of all that data that's being generated from those sensors, you need, of course, to have a lot of compute. So also system on chips from NVIDIA's that are very powerful. I mean, compared to the previous generations with active safety systems that I've been working with, I mean, this is an incredible increase of compute that will be in a car. And that's fantastic, because then you have cars that are super capable, sensor-rich, compute-rich, will be driven all around the world. What can we do with this? A lot of things. We will be focusing on making driving safer, but I'm also sure there will be a lot of other use cases that people can buy on our built on our APIs when you have devices like this. But in order to make sense of the world through all these sensors that create so much data in a very unstructured environment, different traffic conditions, road conditions, lighting conditions, weather conditions, I mean, there's so much variation in the real world. Getting all the data, making sense of that, there lies the power of deep learning. So we are investing a lot of that in order to make sense of the world. In a traditional, or in our previous lives, we've always relied on suppliers that do computer vision. And then you start to send specs forth and back between different companies, and it has been a super slow process. We decided a couple of years ago that no, this is not going to work out. If we want to be fast, if we want to be the best in the world in this area, we need to take control ourselves. So we've taken the decision to do all the perception work, all the deep learning work internally within Zensec. We develop a software stack, what we call from pixel to torque. From a camera pixel, we get a frame and a video stream, we process it through all the deep learning algorithms, we do the fusion with the radars and the cameras, the decision making, and we send out a steering wheel angle and a torque that kind of describe how the car should behave. Everything in between we do ourselves. And the iteration speed we get with this is completely different than earlier. Right now we're building the full stack multiple times a day, we deliver the Volvo cars multiple times a day, while we come from a world where this was done maybe once per 3 months, 4 months, I mean, really slow processes. So the tech that we have allows us to work in a really fundamentally different way. And the faster we iterate, the better the software will get, the sooner we get towards zero collisions. That is really the mission that we are on. And of course, internally, the engineering drops, we build continuously, we deliver continuously. But I think a few years, no, not even a few years from now, next year, when the next gen of Volvo cars will be on the road, that software will also be brought over the air to the consumers. So also as an owner of that car, you will be perceiving how the car gets better for every iteration that comes. Your car gets better instead of worse over time. That's, I mean, just that is a big difference. So what do you need in order to be successful here? We thought a lot about that. And one of the earlier decisions that we made is that we said, deep learning is key for succeeding in this business. We need to be able to do this at an industrial scale. This is not just prototyping or testing. This is really building a factory that can spit out computer vision algorithms at an industrial scale with the right quality, with the right speed, etc., etc. So then, where do you invest? And this was kind of the outcome of that discussion. We said, we need to invest in data. The more data, the higher the quality of the data, the more representative the data set is, the better our algorithms can be. We really need to have data sets and access to data that are representative for driving in the real world. Not only here in Sweden, all around the world. So we're collecting data all around the world, and we have a big factory that is dealing with that. So that is where we have the biggest investment. Then, of course, we need a deep learning infrastructure where we can take care of all the data, train our networks, etc., etc., and also work somewhat on the algorithms. But it's really not the algorithms themselves or the nets themselves designing them. I mean, a lot of them is like public information, and we use what we think is best from there. Most of our work is actually making sure that we can produce those nets at an industrial scale, and that's where we did most of our investments. And it looks a little bit like this now, that we use The algorithms that we use for computer vision, it's very much deep learning, as said, a lot of CNNs, some other networks. And for now, most of the deep learning is actually only used within perception. I think it will change over time. And then we built a very efficient tool chain. We're collecting data worldwide, a lot of driving, automated our pipelines, annotation of training data. We target 2 million images trained. We're not there yet, but we're soon getting there. And then we built a GPU farm on-prem in Kungälv, of all places, with 160 GPUs. And we have a lot of capability there to actually do what we need to do. And that is what we do right now in development phase. As I said, we're not in production yet. It will come. But in development phase, we're running and we have our development vehicles. And we're progressing as it goes. But then in a later stage, we can, of course, also probe data from the consumer vehicles. And then we enter the next phase of our development, and I will come to that. So what do we do then? We have our development vehicles. Maybe you've seen some of them driving around Gothenburg. They have this box on the roof. That's not going to be part of the production vehicles, but this is instrumentation we need in order to collect the right data. We're collecting images, and we're collecting LiDAR's data from those that you see in the roof. And LiDAR gives you range in every pixel, and that's a good additional information. Because then if you have an image, you can overlay the LiDAR, and then you suddenly get distance in your images. And then you have 3D information in an image. And that's, of course, fantastic if you want to drive in the real world. So we're training our networks, and then the outcome, yes, it works, looks typically like this. You've probably seen these type of images before, and we do a lot of that. We recognize vehicles and then 3D bounding boxes on those vehicles, thanks through the smart things we did with the LiDAR. So it's a mono camera. Mono camera doesn't have any depth, but thanks to the LiDAR stuff, we do get this depth out of our networks. And that is true for detecting vehicles, for pedestrians, bicyclists, and of course a lot of other different things. Lane marker detection we do, also deep learning based. The architecture itself is that we have one big network looking at more the lane and road infrastructure, and one network for detecting different objects with all kinds of classifications and segmentations in here. This is another way we can use all the data. Holistic path prediction. So what we do here is here we drive and we try to estimate where is the car going to drive. So we're not looking at lanes or things like that. We're only looking at an image, and we look at that image and predict this is the way that the car is going to drive. So it uses all the pixels of an image to actually make that prediction. And that's a very powerful tool, I think, that we can later on use for vehicles that maybe, or for roads that maybe not have good lane markers or good infrastructure. And the way we train it, of course, is that we know when we train, we have information about the future. So we know where the car has been, and then you can train these kind of things. As said, segmentation. And here, for example, we can estimate free space. If you want to drive, if you want to operate a self-driving car, you better be really, really sure that the space in front of you is empty and drivable. So we detect that there are no objects, but we also actively detect that there actually is a drivable surface in front of us. And we could do it with things like this. And as I said, we have a lot of cameras and we do all this kind of stuff, but it needs to be fused with other sensors. LiDAR is one of them. It will also be part of a production vehicle. And this is, I was hoping to have a film, but it actually only became an image. But we, in the last few months, had a couple of engineers, just not even a handful, I think there were 3 or 4, that started to apply this deep learning tool chain that we built, this big investment that we did. They started to apply this also on LiDAR data to detect objects and lanes and other kind of stuff. And it, to be honest, it really blew me away how 3 people using our tool chain could get super good performance out of this. For me, it was proof that we have a super good tool chain and proof that we have really good colleagues. And the result was really impressive. And we need that because we need to combine cameras with LiDARs, with radars, and all the other stuff to be able to drive in a sufficiently safe way. So, as said, we are in a development phase, a lot of cool stuff, but we want to put this in production vehicles. We want to use this cool stuff to actually make an impact in real life. And we're going to start with that in the next generation of Volvo Cars vehicles. They will have, as said, a lot of these sensors, a lot of compute, and we're going to deploy that. And I think then the interesting phase becomes, because these vehicles, they will be out on the road. Consumers are driving them every single day. We will probe data from those vehicles, probe data about where the car does automatic emergency braking, where it maybe does not do automatic emergency braking, when they crash and we've never seen it. All this kind of data we can probe. When we're unsure about detecting mooses on the road, maybe we can probe for candidate images on where there is a moose. And then we can get that to our data factory, we can do some annotation, train our network, push the new generation of software out there. And the faster we can iterate using a fleet of vehicles, I mean, it will be 100,000 millions of vehicles all around the world being used in all weather conditions, all types of roads. I am convinced that this is the method to get towards zero collisions. And we will do that. This is the infrastructure that we're building up. The production start is not so very far away. We will start small. From there, we iterate. We'll iterate for collision avoidance features, but also for self-driving car technology. Because self-driving cars, they won't just pop up everywhere at any point in time and usable all the time. We will start small, somewhere. We will start on highway driving, traffic jams in California, because there it's sunny and it doesn't rain and snow, it's easier. But we will start there. But those vehicles will be there all around the world. So also there we will probe and try to understand what is the next phase. How can we increase the operational design domain? Go from California to New York to Sweden to China. How do we go from only traffic jam driving to high speeds driving? We will increase through this loop, the same kind of loop, probing data from the devices, if you want, and improve our products. And then we'll find things like this. We will find it is difficult to drive in exhausting conditions. We will collide with road debris or drivers will do it. I mean, there's many use cases where today's collision avoidance systems cannot help a driver. Tomorrow, we will be able to do that because we will probe all this data. As said, we go towards zero collisions faster. Some key things to do that is we are working a lot with safety, with traffic safety, but also with system safety. Proving that something is sufficiently safe requires data. Data is the only thing that we trust here. And we're going to probe that, and we're super dependent on that. Then over time, we will increase or improve the availability of the features, as I said. We'll improve its performance. It will grow the ODD. That's a lot of focus on us also. But then when it comes to AI and deep learning specific, also here, I think we're only scratching the surface. Because right now we use deep learning to frame by frame extract relevant information out of images or out of a LiDAR point cloud. But over the coming years, I think we will also use deep learning for tracking objects over time, get the temporal aspects of driving in video streams into our neural networks. We will start to use it for predicting how people drive. So right now, let's say a pedestrian. We detect there's a pedestrian. We have no clue on what that pedestrian is going to do 2, 3, 4 seconds from now. We can make some like Newtonian predictions, like if you have a speed, you will probably continue with that speed. But with deep learning, I think we can get much better predictions how pedestrians will behave, cars will behave, and based on that information, of course, we can make much better decisions. But then, maybe even one step further is that we will do completely different ways of end-to-end learning, where we actually go from an image all the way to maybe a trajectory that the car is supposed to drive. Try to train everything in one big neural network. I know some startups are experimenting with that. We're not really using this yet, but these are next steps that we are going to do. So there's tons and tons of opportunity to really deploy deep learning at an industrial scale, making a difference, bringing cars towards a place where collisions do not happen anymore. Thank you.
Thank you. Thank you. So, do you have any questions from the audience? I'm sure there are. So, here we go.
Hey, thank you, Leon from RISE. You talked a little bit about the hardware in use, and you specifically named LiDAR as a very important part of the hardware package.
Yeah.
Another company from California has famously stated that they can do it all with just cameras. And they recently ditched even radar from their cars. So I'm sort of curious, what's your take on that? I mean, as humans, we can drive just by vision, and we do a fairly good job as long as we're sober. So, but the cars seem to need LiDAR, in your opinion. So, yeah.
Yes. Yes. From a first principles, I agree. One eye, I can drive a car with one eye. So one eye and a lot of compute is in principle enough to drive a car. But cars don't drive in principle. You need to make it real in the real world. Tesla doesn't have the technology to drive unsupervised. They have a very capable car, but it's not unsupervised. You cannot read a book behind the steering wheel. You cannot fall asleep behind the steering wheel in a safe way. All the other companies that make the bet use a LiDAR, and for good reasons. Real world is messy. It's super hard. Cameras have their limits. AI has the limits. AI is not as good as our brains yet. If you want to make the real step towards unsupervised driving, you need a LiDAR. And we're going to show that, and in that way beat Tesla.
I guess you've had that question before.
Yeah, of course. I mean, we also think about it ourselves. I mean, if we can do it without a LiDAR, it would be fantastic.
Yeah.
But there's no data that shows that you can do it.
Yeah. So, yeah. We had a question over there.
Hi, Claudia from Spinit. I have a question regarding safety. It rang a bell when you talked about predicting behavior, behavior of other cars, behavior of people. Because I recently came back from Latin America. Don't take me wrong, I love my continent, but you cannot compare driving here in Sweden or driving on a road on the States to what it is driving and the behavior, not only when people are drunk, but also when people have other beliefs, other cultures, other way of acting. And I guess some people in other continents can relate as well. If you want to make this into a large scale, I think that needs to be considered. What are your thoughts on behavior?
Behavior is, of course, super important. I mean, just on a general level, if you want to get to a traffic system without any collisions, you need to also have people that drive in a responsible way. Drive when they're attentive, not sleepy, not drunk, and things like that. And I know that's different cultures, if you want, in different markets. But from a technology perspective, as we develop it, we develop for a global market. I mean, the previous systems that we designed are being deployed in all the different markets around the world. And they work, at least when it comes to the assisted type of technology. That works really well. I mean, if we are about to have a collision and there's no reasonable way in which you can avoid it, our systems will brake the car. And maybe in some countries it will brake more often than other countries, but the principle, physics is still the same. Then when it comes to deploying self-driving technology, then it may be different, because it is, of course, easier to have a self-driving car in a well-organized highway with well-behaved vehicles in low speed. That's easier to start there. And it will take a long time before we are driving autonomously in the middle of, I don't know, maybe it's a country or a city in Middle America where there's a lot of pedestrians and other types of driving behavior. That is not the place where we start. I mean, I want to get there, but it will be a journey before you can operate self-driving cars in those types of environments.
Thank you.
Thank you. So, unfortunately, that was the last question for Erik.
Good.
Thank you.
Thank you.